So what we have done yesterday, right? So yesterday we talked about bifurcation diagrams, okay? And I think this is a point in our course where I feel more or less confident that if I just stop at the course right now, stop it here, okay? Most of what we are going to talk about now is like more advanced stuff or things that you're not going to find all the time, but of course it's useful to learn and to know, okay? But then I feel like a lot of stuff you learn as you go, okay? So when you're going to work on your project, okay, and work on your own problems, of course what we studied so far is not, everything is not enough to overall situation, right? So, but then the specific analysis for each model, each situation, and so on, are usually tailored to the analysis that you need, right? So if you want to study, I don't know, transients, then you need some different kind of analysis. If you want to study something with many parameters, it's some different kind of analysis. If you have so the specific analysis you're going to do in your own projects, in your own problems, either here or in real life, like the real research. Not that here you're not doing real research. It's real research, but it's kind of toy research, right? So it's research that you include in a month, right? So, but then, so I think these are the basic tools already. So you already got a good foundation. And now we are going to look at a series of more specific techniques, okay, or more specific ideas, okay. They can help you to get a good grasp of stuff that you can do. Is not that every problem, because what we've done so far, like every problem, you're going to do numeric integration, you're going to have to do simulation, you're very probably going to do some kind of bifurcation diagram or something like that, right? So this is very, very, very common, okay? But then now we are going to start seeing more specific examples and stuff that can be useful. It's not in every problem that is useful, but it's very common, right? And you can adapt to specific situations, okay? So, yeah, that sounds good, yeah? So another thing is that yesterday we reached the middle of the course, right? So we have a total of 20 classes. We had 10 already. This is the 11th one, right? And so I prepared a form for you that I should have put the link here, but I didn't, so maybe I will, let's see if I can find it. And that I want you to fill by tomorrow, right? So that we can, it's very easy, right? So it's not an exercise, it's just to see where you are, right? So let me copy it here. This is the link. Well, now I have to copy this. This is very ugly, right? But I think it beats having to log into my account and so on, right? So WCPRJ yeah, let's hope this all works. Okay. Okay, here it is. So just to see where you are in each exercise and see if it is worth to maybe post some of the solutions of the exercises of the previous exercises on Slack, or maybe use some of the class time for those exercises and some general feedback. Okay, so I post this link over here. So I want you to exercises and the course in general. Okay, so please answer until tomorrow. Better, no? Tomorrow is yeah, it's 25, right? Yeah. Okay. So here's the link here. Okay. Okay. Yeah. Can you please do that? What? I don't follow. What's the problem? Okay, sorry. Yeah, I'm still talking, right? So in a moment, so it's in the links, right? So it's in the links file here, okay? Yeah, so, yeah, because I showed the form, right? Yeah, let me show the form again. Yeah, sorry. So here it is, right? It's just a question of which of the exercises you were able to finish or not, and why, and so on, and then you can write some general feedback, because we're right in the middle, so we still have some time to change something if something's not working so well, and so on, okay? Yeah? Comments, questions? Well, if you have more general things, and also write down over there, okay? But please answer this by tomorrow, right? So that I can think about it for how to follow up on the course, okay? Okay, so then let's move on then for today's class, yes? So today we are going to explore, to learn how to explore phase spaces and parameter spaces, okay? So this is, what is when I say things like this, a space, I feel like this could be unfamiliar to many of you, right? So a space is just like I have an axis, this is a space. I have 2 axes or 3 axes, this is a space, okay? This is just a region of possible values of parameters or of initial conditions or of something, okay? So this is a space, right? So if I just draw the plane, this is a space, right? Yeah. So it's just a general term for sets of values that can change, yeah? Okay, so this is satisfying definition, okay, of what is the informal definition of what is a space, okay? So the idea here is that it's quite common for you to have to work on problems that are bidimensional, okay? So, or more, maybe even more dimensional, but at first bidimensional, okay? So, then a tool that is very useful is to be able to plot heat maps, okay? Everyone knows what is a heat map. Well, we'll see examples in a bit, okay? So, it's essentially when you have a 2D plot, right? Like this here, and in here, instead of having lines, I have colors. So it's also a color plot, okay? I just put colors here. So each point has a different color, and the color usually means something, right? So the heat map is usually because this was used to represent heat, right? So if I have I don't know, a bar that is heated in one point and cooled at the other end, then the color goes from, I don't know, blue to red or something like that, right? So, yeah. So this is a heat map or also a color plot, okay? So let's do some examples here. So this is a very practical tutorial, right? So the first one is I want to color some triangles, right? So I will do something here. Let me plot this so it's simpler, right? So I'll take first an example that has nothing to do with, I don't know, differential equations. And so I'm just trying to plot it to color some triangles in the plane. Okay, so let's wait for it to. So I have here on x that is goes from 0 to 1, and then I plot the identity line, right? So y equals x. Okay, maybe let's turn off this light here. Why it's. Right, so this whoa. What's oof. Did I do this right now, or was it like that before? Wow. Okay. Okay. So here it is, right? So I plotted 2 lines. One is the blue line, that is the identity line where x equals to y, and another is the same one and the opposite diagonal, right? So this is where x plus y equals 1, right? Yeah. Or where y is equal to 1 minus x, okay? And then these 2 lines, we divided this region here from 0 to 1, 0 to 1 in 4 regions, okay? I call this 1, 2, 3, 4, okay? Yeah? And I just want to say, well, I want to plot a color plot or heat map that colors differently these 4 regions, okay? Yeah? How do I do that? Of course, when you, Matplotlib has some functions that allow you to say, okay, you can color from a certain line up to a certain line, and it can already fill the whole region for you. Right? So this is the smart way to do that, okay? But I'm not going to do the smart way. Why? Because in many problems that we're going to find, we don't know where these lines are, okay? So maybe, well, we'll see examples later on, right? But maybe I have to go point by point along this plane and see where it fits, it goes into one category, where it goes on the other, okay? Yeah, so this is more or less common, yeah? Okay, so let's try to do this then in the dumb way. Okay, what is the dumb way? Well, I will check if a given value, right, in a given point x, y, is above or below the blue line, and if it is above or below the green line. Yeah. So if it is above the blue and above the green, I have the 2, I'm here. If I'm above the blue and below the green, I'm here, and so on. Yeah. Does that sound easy for everyone? Yeah? Questions, comments? It's okay, yeah? So I have to find where each point is, I have to check if it is above or below each of the lines, yeah? Okay, okay, so I have these 2 conditions here, right? So if it's either above or below, I check if the value of y is greater or lower than the value of x to check if I'm here or here. And if x plus y is smaller than 1, I'm down here. If it is larger than 1, I'm up here above the green line, okay? Okay, so let's do this now, right? So how do I do a heat map, right? So I'm going to have a set of points for the whole plane, okay? So I have to have, so I will have an array of x's and an array of y's, okay? And I'm saying here that I'm going to do a spacing of 0.1 here from 0 to 1, okay? So it's 0, 0, 1 up to 0, 9, okay? Okay, but then I have to plot a polar map. It's not enough to just have the points along x. I have to have a grid of points, okay? I think we had an example like this when we plotted a surface some time ago, right? So I have to have a grid of points that tells me, well, here, so I suppose that, let me plot this with a grid, so I think looks nice, right? Yeah, so like this. So suppose that I'll put my points over the points in the grid here, okay? So in this point I have to say, I have to have an array of x's that tells me that this point has value of x0, this point also, this point also, this point also, this point also, and this point also. And this point in the grid is x0 to 0, 2, this is 0, 2, this is 0, 2, and so on. So you need a matrix or a 2-dimensional array for x and another 2-dimensional array for y as well, right? And the combination of these 2 gives me all of the points in this grid, okay? So let me run this. So what does this do, right? So this represents the points along x that I want and the points along y, okay? And now this 2D grid is written like this. I use this function called mesh grid. And to see what it does, I'm going to print what is created here, what is x and y, okay? So let me run this thing here, okay? So this is what is the x grid looks like, okay? So this is all the columns have the same values, right? And it changes along the columns, okay? Not along the columns, it changes for each column has a different value, okay? It changes along the line actually, okay? And for the y grid, it's pretty much the same, but it's transposed, okay? So I have, of course, it's not just transposing one from the other, because if I had here in y a different grid, okay? If I had, I don't know, I would have a grid that is not the same spacing, right? So if I did it like this, yeah. I could have a grid that has more points along y than x, right? So they are not exactly the transposition of the other, one of the other, okay? Yeah, I didn't have to use the same spacing, okay? Okay, so, but let me go back to that because I think it's nicer. Okay, so far so good, yeah? Yeah, questions, comments? Okay, yeah. Mike, where's the mic? Okay, yeah. This is something to tell me the shape of an array, okay? So it's a property of the array. Yeah, so this is a 10 by 10 array, so this is 10 by 10. It tells me the shape. Yeah, this is very useful, yeah. I thought I had mentioned this before, but maybe not. Yeah, thanks. Yeah, it's too much to remember all of it, yeah. Okay, so this is very useful because then we know how many lines, that is the first number, and how many columns, okay? And of course, the two of them have to have the same shape, okay? So if I go here again, and I divide y by 2 here, okay, dy by 2, I have now shapes that are 20 lines by 10 columns in both arrays, you see? Yeah? Okay.
Why isn't the y grid?
What?
The y grid, the second one.
The second one?
Yes. Why isn't 0 at the last line? You know?
Sorry? I think I don't follow. What is?
Like I thought that the y grid
Yeah.
have to have the zeros closer to the last line, you know? Instead of
Okay. So yeah. So it's the matrix is represented by. It starts with 0 because it follows the order of the little y over here. Okay. So it starts with 0 and goes up to 5 to 1. Okay. Yeah. So it starts with 0. So the first line will be 0, and then it goes up to 1. But when I plot it, just when I plot it, then the 0 is down. Right, so it turns off when you plot it, then you take the y and invert it because it, not because I invert it, but because it doesn't matter the position in the array. It matters the value of y in the array. You see? So if I wrote this as I can even do that later, right? So I would write down this y here in the reverse direction. I would start from 1 and go down to 0 and have the same numbers, okay? Would it plot different if it was 1 and then 0.9 and 0.8 up to 0? No, because it follows the values of y, you see? Yeah? So it doesn't matter.
the order inside
Yeah, it doesn't matter the order.
the array,
It doesn't matter, yeah. Yeah, I think for the plotting function, it usually wants it to be ordered in the sense that you have the values of x and y being either increasing or decreasing, but you don't have to. But it usually follows. Yeah, you see. But I'm not even entirely sure about that actually. Maybe it accepts any order at all. I don't know. And I never try to use an unordered, a mixed order, okay? Because it doesn't show up, right? But then, yeah. Okay, so more questions? More comments? Okay, so going back here, so we have these two arrays over here, okay, these two grids for x values and y values. And now what do I need? I need the z value, okay, or what is the value of the for each point, right? So I have, for instance, if I look at a position here, so I'm taking this point in the grid here, 0, 4, 0, 2, okay? So this 0, 4, 0, 2 here corresponds to the 50 value here in the x, right? So this is, and to the third, or maybe let's take some closer to 0. So 0.2 and 0, okay? So this one here. So this is the third value here. So 0, 2, 0 here, and this is 0 for y here, okay? So this is the position I, the index along the line is 0, and the index along the column is 2, right? So this has ordinates 0.2 and 0, right? Okay, so I want you to know at this point what is the color of it, right? So I have to look at these values of x and y and check in which region it is, okay? Yeah, and then I need to have so then I need another array, another matrix that will keep the value for each point. If with each point I want you to know if it is 1, 2, 3, or 4, which region it falls into, right? Yeah? Okay, so then my next step then is, okay, I create an array called Z that has the same shape as X, okay? So this is the way to do it. This is one of the ways to do it, okay? So I create an array of zeros, and the shape of this array is the same shape as the shape of x, okay? So x dot shape is 10, 10, and this will be the shape of z as well, okay? Okay, and now I'll just loop, okay? I'll just loop over all of the points and look at each point and determine where it is, okay? In which of the 4 regions, okay? So I will loop over all of the lines. How many lines I have? The x dot shape 0, okay? So the first value of the shape, the first 10 there, is the number of lines. And the second value, x point dot shape 1, the second value is the number of columns, okay? So this is I then is the index of the rows, and j is the index of the columns, okay? Good so far? Yeah? So I have 2 loops here, and now I have to do the checking, right? So if x is smaller than y, right? Or maybe y is greater than x, I'm above the blue line, okay? And then I have to check, well, if I'm above the blue line, but below the green line, I'm in the region 1, okay? Above the blue line, below the green line, I'm in 1. If I'm over the blue line, above the green line, I'm in the region 2, okay? So I have some ifs over here, okay? So I'm either in region 1 or 2. And then there's an else here, so if I'm not above the blue line, I'm below the blue line, okay? And then I have the other 2 cases where I'm either in region 3 or 4. Yeah, okay? Okay, and then for each step here, I set the value of z, okay? Z is either 1, 2, 3 or 4, okay? 3 or 4. So the whole matrix z, let me run this at the end here. Let me also print z over here, okay, at the end. So you see I have 4s here, 1, 2, 3, 4. You see that compared to the plot, it's kind of reversed the y, right? Yeah? So you see that it's actually 1, 2 is up, right? So 2 is up, and 4 is down, right? And 3 is in the right, okay? Because this 2 here is when y is close to 1, that is down here actually, right? But when I plot it, it should probably work, okay? And then there's this function called pcolor that is a color plot, okay, or a heat map, okay? And I just pass the 3 grids here, x, y, and z. I have a label and I have a color bar that is the scale of the colors, okay? The scale of the colors. And here it is. Huh. Well, I don't know. What do you think? It's kind of ugly, right? Yeah? Kind of ugly. But, well, it's more or less alright. More or less, right? So 1 is here, you see 1. 2 is up here, 3 is right here, and 4 down here, okay? So these are the 1, 2, 3, 4, right? So it's almost alright, but what is the problem here? Is that we didn't pay a lot of attention to what happens exactly over the diagonals, okay? When x is equal to y, or in x plus y is equal to 1, right? And then it colored in one color, but maybe it shouldn't have any color at all, I don't know, right? So it's, but then usually you don't know exactly, so in most problems, you don't know exactly where the line falls, okay? This is a very untried example, okay? Usually you don't know exactly where the line follows, so you have to test point by point. And if you don't want these jagged things here, what do you have to do? To decrease what? The steps here, right? So instead of having these large steps here, I want to have very small steps, yeah? Yeah, so I go back here then, and let's redo this now. All of this with a smaller spacing, okay? So maybe 10 times smaller is okay? Yeah, let's try that. Yeah, so 10 times smaller. Now the print here gets really long. And now this thing here. Yeah, better, right? Better. Yeah, acceptable, not acceptable, what do you think? Yeah, I could make it even better if I wanted, increase even more the time, the step size, okay? Yeah, but I think this is already acceptable, yeah? So you see that for a small step size here, the diagonal doesn't matter so much, right? So it doesn't, you cannot really see that this is a little bit above the diagonal, this is a little bit to the right. If you look very carefully, you will see, right? But then it's a really small imprecision here because I included the diagonals in one of the sides, right? So yeah, okay. If you want a more refined code, you can check for equality or given a tolerance and so on, but this is usually not even worth doing usually, right? Okay. So, okay, this is fine, but this out here is quite ugly, right? It's quite ugly because I have to keep following this loop, and it's kind of, well, you know by now that loops can be confusing, right? So these loops, you get you mess up, and then you invert what are columns, what are lines, what are the indexes, and so on, right? So there's a smarter way to do this that is still very general, that instead of having, so what is the core thing here? Is this, the thing inside the loops is given a pair of values x and y, tell me to which region it belongs, yeah? So I'm going to take this and write this as a function, okay? And write this as a function, right? That returns the value that I want, right? And then instead of doing a for loop, I will make this function take a vector as an input and apply this function to all the points in the vector, okay? In all the points in the array, okay? Does that make sense? So it's like when we had, for instance, the NumPy functions. The exponential, if I apply the exponential function or the sine function to an array, what does it do? It applies exponential to each of the elements, okay? Now I have a 2D array, a matrix. What I want to do, I want to apply a function for each point and make it tell me what is the value of z here for each one of those points, okay? Make sense? Yeah? So let's do that. So I'm going to use a function. So this function is essentially copy and pasted the above over there, so, but instead of having to care about x, y, x, I, j, y, a, I, j, and so on, I just said, okay, little x and little y here, that are arguments of the function, okay? And then if I have x smaller than y, I have this, and so on. This is exactly the same, okay? And then instead of setting that z is this value, I return this value, okay? Return 1, I return 2, or return 4, return 3, yeah? Okay? And then I'm going to call this function. Right? So with this function here, I can, for instance, before doing this, right? So if I try to do this, so I want to do this for all values of x and y, right? Yeah? Of course, if I, instead of do this, I just do something simpler, right? So instead of, if I look for instance, check region for the point, I don't know, point 2, point 3, right? It tells me that this is in the region 1, okay? This is point 2, point 3 is over here, right? So this is region 1, yeah? Point 3 is here, so region 1. Yeah, okay, it works, okay? But then if I try to pass this to this, not just a single pair of values x and y, all of them at once, right? This is not a good thing, right? Because what is happening inside this function now, right? Right now, x and y are two-dimensional arrays, they are matrices, right? And when I try to do if is analysis, right? So when I do comparisons with arrays, right? This doesn't work so well, right? Because I can do x, big X is smaller than big Y, right? Let me print this. So if I do this, right? With the matrix, you see? What does this return? This returns me an array, right? A 2D array of falses and truths. Yeah? So for each point, it compares the value of x at that point with the y value at that point. Okay? So this works. But then if I do an if with this thing here, then it doesn't work because it doesn't know, well, which one I use, okay? Do I use this or that, or do I take an and in that, or for all of them, an or how do I combine all these values, okay? So this doesn't work, okay? So I cannot just call my function on all of the values at the same time, okay? Okay, so then what do I do instead of that? I have to make this function check region. When it takes a vector, I want to force it to apply the function to each element one by one, yeah? And for that, NumPy has a very convenient function that is called conveniently enough, it's all vectorized, okay? So you vectorize a function. What it means vectorize a function? This means take this function and change this function in such a way that now the arguments of the function are going to be interpreted as arrays, and then you will apply this function to each element of the array, right? So if you have a function, because for instance there are functions, if I had a function here that is just, I don't know, returning, I don't know, x squared or x times y, right? It works element by element, okay, it doesn't care about it. So you don't have to vectorize this function because it's automatically vectorized already. But if you have a function that has an if else and this kind of stuff, right, that is not automatically vectorized, you need to do stuff like this. You need to vectorize the function before using it, right? So I'm going to have this, right? So now check region will accept arrays as arguments, okay? And now this works, right? So, right, and now if let me print z over here, but now I have a small timestamp, right? So yeah, 1s, 4s, 3s, 2s down there, okay? Yeah, so now this works, okay? And now I can I plot it exactly the same way, okay? So this gives me exactly the same result as before, but it's more clean, right? Because I just write a single function for given an x and y, vectorize this function, and apply this function to the grid that I defined earlier, right? So this is usually easier than writing all the for loops, okay? And probably more memory computationally efficient as well, right? So I won't go into this stuff too much, but usually this is a better approach in computational terms as well, right? Okay, good. Everyone with me so far? Questions, comments? Okay, so now for the first exercise of today, right? So now let's try some real world example here, okay? Real world in the sense of, well, whatever Roberto is teaching over there, right? Yeah? Okay, so let's look at basings of attraction. Have you heard this term basing of attraction? Yes or no? Roberto has thought about this already or not? Basings of attraction? Yeah? Okay, so we had this logical competition model, okay, so you are already very familiar with this. But then there's a situation here that if both alpha and beta, they are both large, okay, there's very strong competition from both sides, okay. You have that situation when if you start with a lot of n1 and little of n2, n1 wins the competition. If you do the opposite, you start with a lot of n2 and small numbers of n1, then the species 2 wins the competition. Okay, so the final state depends on the initial conditions. Okay, then I want you to think. Okay, let's then find for which initial conditions do I go species 1 wins, for which initial conditions species 2 wins. Yeah, so this is the question, right? So then this is what I want you to do now, okay? I want you to use what we have looked at so far. So what do you have to do? You have to write a function that takes an initial condition, solves the equation, solves the differential equation. So I think you can use, we have solved this equation already, right? Some last week, right? So you can just copy code from last week's tutorials. Solve this differential equation for some time and see if the final solution is close to one of the fixed points or the other, okay? And then it returns a number that says, well, species 1 wins or species 2 wins, right? And then you have a grid of points, you set up a grid of points and plot a map of, or plot a color plot that tells me where, for this region here, solution 0 to 1 fixed point, for these other points here, the solution goes to the other fixed point. Yeah, so I have a pretty picture. I do more like I pretty much exactly I'm drawing the basis of attraction. Okay, one basis of attraction will be one color, the other will be another color. Yeah, does that make sense? Yeah. Okay. So yeah, so we have work. So this is for you to try to do now. Everyone understood how to start? Yeah. Questions? Okay, so let's work. Yeah. is that if you have the two species exactly equal in all parameters, right? So R1 equals to R2, K1 equals to K2, alpha equals to beta. So all the parameters are the same for these two species, right? Then this line dividing here should be exactly the identity line, right? So this is a straight line dividing the regions, okay? Another thing that is also helpful for other situations is that this line dividing the two regions, that is all the separatriz, right? I think Roberto told you that, yeah? Separatriz. So the separatriz should cross the unstable fixed point. So if you calculate the value of the other fixed point, the unstable fixed point, it should be somewhere over this line here, okay? So it should be somewhere, I don't know. It always falls, even if it is not a straight line, in all situations, it should always cross this point. So you can always also plot this point and see if your separatriz is crossing this point, okay? Good, so yeah, so we finished for today, yeah. So I think there's another example, but then we don't have time to go over that today, yeah. So, but I think the other one is actually simple.